In these next questions, let's go even farther. We want to state the null and alternate hypotheses, and we also want to give the proper conclusions for the test. So there's a lot of information in these setups. Some of it is useful and some of it is not, and we have to sort of dig through it and know what do we need to write the hypotheses and what do we need to give the conclusions. So problem number 3 says, random samples of students at 2 different community colleges were taken to see how many televisions were owned in each household. Each individual was randomly chosen independently of others. One of the schools is in a wealthy community, MC, while the other school is in a less wealthy community referred to as OC. From MC, 30 students were surveyed with a mean of 3.1 and a standard deviation of 1.49 TVs. And from OC, 30 students were also surveyed with a mean of 3.9 and a standard deviation of 1.49. The hypothesis being tested is that the mean amount of TVs is not the same using a significance level of 0.05. T came out as negative 2.079 and P came out as 0.042. Okay, so the first thing we want to do is write the null and the alternate hypotheses. So let's start there. Oops. Okay. So I'll write H sub naught, H sub A. I'm immediately drawn to this phrase here that we are testing. The hypothesis being tested is that the mean amount of TVs is not the same. So that leads me to my alternate. We're testing that they are different or not the same. We are using a not equal to sign here. And what we have is we have the mean value of TVs for the MC community and the mean value from the OC community. So I'll use MC and OC as my subscripts. So when I back up, then what I must be assuming for my null hypothesis is that the mean amounts are indeed the same. Oops. So with an equal to sign, mu sub MC equals mu sub OC. Now we're going to skip all the middle. We haven't got to the middle part yet where we're actually going to eventually run all of this ourselves. They're skipping that. They're telling us what got spit out of the program, and it tells us what the T value is and the P value. The T value is good information to have. A lot of times you need to enter that value as part of your answer, but ultimately the conclusion is drawn based on that P. So notice here we have P equaling 0.042, and remember that the alpha value we are told to use in this case, the significance level is 0.05. So we have to compare those two. How does 0.042 compare to 0.05? Well, it's less than. So we can say for our conclusion, since P is less than alpha, we reject the null hypothesis. We can conclude that there is enough evidence to support that the mean number of TVs per household in these communities is not the same. Let's look at one more of these. A study is being conducted to test whether male college lacrosse players have fewer broken bones during their collegiate career, on average, than male college hockey players. A random sample of 35 male college lacrosse players had a mean of 4.24 broken bones with a standard deviation of 1.12, and a random sample of 30 male college hockey players had a mean of 4.96 and a standard deviation of 2.27. Suppose that alpha equals 0.05 and the p value comes out greater than that. Okay, so let's set up our null and our alternate. The test specifically is saying they're trying to show that male lacrosse college lacrosse players have fewer broken bones. So it looks like we have a less than for our alternate hypothesis, and we would be trying to show that the mu of L for lacrosse is less than the mu of H for hockey. So then my null would be the complement of that mu of lacrosse is greater than or equal to mu sub hockey. We're given the information that P came out greater than alpha. So we can skip straight to saying since P came out greater than alpha, we fail to reject the null. There is not enough evidence to suggest that male college lacrosse players have fewer broken bones than male college hockey players.